Somewhere in the depths of space, an explosion may already be occurring, the light of which has not yet reached the Earth. It doesn't look like an ordinary flash of a star. It doesn't look like the birth of a new nebula. And it doesn't look like the slow fading of a distant sun. This event may last only a few seconds. But in those seconds, it can release so much energy that the usual idea of a cosmic catastrophe becomes too faint. The most alarming thing about a gamma-ray burst is not only its strength. The most alarming thing is its direction. If a narrow stream of gamma rays ever turns out to be directed directly at Earth, the planet can only know about it when the impact has already reached the atmosphere. A gamma-ray burst cannot be seen in advance as an approaching asteroid. He does not fly through space slowly, leaving time for calculations and anxiety. Its radiation travels at the speed of light. This means that the first signal of danger and the danger itself come almost simultaneously. There may not be a life-saving gap between detection and impact. Space in such a scenario does not warn in advance. It simply flares up, and in a moment, the upper layers of the atmosphere are already taking over the flow of energy born in the catastrophe of a distant star.
Gamma-ray bursts are among the most powerful explosive phenomena known to modern astrophysics. Their energy is concentrated not in soft visible light, but in gamma radiation, one of the harshest forms of electromagnetic radiation. This radiation carries enormous energy and is able to interact with matter at the level of atoms and molecules. At great distances, it becomes weaker, but if the source is powerful enough and the beam is pointed exactly towards the planet, even a distant event can turn into a cosmic threat. The origin of gamma-ray bursts is associated with the most extreme moments in the life of matter. One of the main ways of their birth is the death of a very massive star. When such a star exhausts its internal fuel, its core can no longer maintain equilibrium. The outer layers still exist, but inside, the catastrophe is already beginning. The core shrinks, the density increases, the matter falls to the center, and an object with gravity so strong that the space around it changes the very structure of the motion of matter. Under such conditions, a black hole can be born.
But a gamma-ray burst is not just a star exploding in all directions. Its most dangerous feature is that energy can escape in the form of narrow streams, similar to cosmic jets. These jets pierce the dying star from the inside and rush outward at almost the speed of light. In them, matter is accelerated to extreme speeds, magnetic fields twist, shock waves collide, and particles receive colossal energy. It is these directional flows that make a gamma-ray burst particularly scary. All the power of the event is not dispersed evenly throughout space, but can be compressed into a relatively narrow beam. If the Earth is far away from such a beam, the event will remain a distant flash recorded by instruments. But if the beam is looking directly at us, distance becomes the main question. Not every gamma-ray burst is dangerous. Most of them occur in distant galaxies, at distances where their radiation arrives at Earth already too weakened to cause a catastrophe. However, the universe is huge, and the Milky Way contains many massive stars, binary systems, and remnants of stellar evolution. Somewhere among them, there may be objects that may one day end their lives so that the direction of their final ejection will be decisive.
There is another way in which a gamma-ray burst is born, the collision of compact stellar remnants. As two neutron stars orbit a common center, they slowly lose energy and move closer together. Their orbits are compressed, their speed increases, and the space around the system is filled with gravitational perturbations. At the final moment, the two super-dense masses collide, and matter falls into conditions that are difficult to describe in ordinary words. there is a brief but incredibly powerful burst of energy. Such events are associated with short gamma-ray bursts, sometimes lasting less than 2 seconds, but their brevity does not make them faint. On the contrary, it is the suddenness and density of energy that make them especially mysterious. Gamma-ray bursts are divided into long and short. Long ones are more often associated with the collapse of massive stars, short ones with the merger of neutron stars or other compact objects. But this classification does not explain everything. Some spikes do not behave as expected. Some have too complex a signal structure, others have a strange afterglow, and still others have energy that goes beyond the usual patterns. Sometimes the flash seems short but has signs of a different origin. Sometimes a long event appears where there shouldn't be a young, massive star. Each such oddity shows that gamma-ray bursts are not fully revealed.
After the first gamma-ray burst, there is often an afterglow. It can manifest itself in the X-ray, optical, infrared, and radio ranges. This afterglow is born when the ejected stream collides with the surrounding interstellar medium. Matter accelerated to near the speed of light crashes into gas and dust, creating shock waves. The particles are accelerated, the magnetic fields are amplified, and the radiation continues after the main impact. For a distant galaxy, this could be a trace of disaster. For a planet in the line of the beam, the main impact would have already occurred before the afterglow was an intelligible sign. For the Earth, the most dangerous thing is not light itself in the usual sense. Gamma radiation would interact with the upper atmosphere. Air would have been the planet's first protective shell, but this protection would not have been without consequences. High above the surface, gamma photons would begin to break down nitrogen and oxygen molecules, trigger chains of chemical reactions, and create compounds capable of destroying ozone. The ozone layer plays a crucial role because it traps a significant portion of the sun's harsh ultraviolet radiation. If it weakens sharply, the Earth's surface will be under more severe solar radiation.
The main catastrophe after a nearby gamma-ray burst could not be the instant burning of the planet, but the slow destruction of living conditions. This makes the threat even more insidious. In the first moments, the surface might not have looked like a scene of total destruction. The Earth would continue to rotate, the oceans would remain in place, and the continents would not disappear. But the atmosphere would have already begun to change. Ozone would be destroyed, ultraviolet levels would rise, and the chemical composition of the upper layers of air would change. Life, especially vulnerable to radiation, would begin to experience pressures that cannot be stopped by conventional means. Organisms that depend on light and the upper layers of the ocean could become especially sensitive. Microscopic life in water, photosynthetic organisms, the basis of food chains, all this could suffer from a sharp increase in ultraviolet radiation. If the blow is strong enough, the changes would affect not one area, but the global biosphere. The effects would spread through climate, atmospheric chemistry, ocean ecosystems, and food chains. A gamma-ray burst in such a scenario would not just be an astronomical event, but an external blow to the entire system of life.
There is a hypothesis that such an event could be associated with ancient mass extinctions on Earth. This is not a proven fact, and there is no exact certainty here, but the opportunity itself is important. If a directed gamma-ray burst occurred near the Earth sometime in the past, its trace could remain not as a crater, not as a layer of molten rock, but as a biological rupture, a chemical anomaly, and a sharp change in conditions on the surface. Such a catastrophe does not leave a simple trace that can be seen immediately. Its imprint can be scattered throughout the atmosphere, oceans, and evolutionary history. The most frightening feature of a gamma-ray burst is the lack of the usual protection of time. The threat from an asteroid can be calculated if the object is detected in advance. A solar storm can be seen by the activity of the sun. But a gamma-ray burst from a distant stellar catastrophe announces itself only by its radiation. It is impossible to receive a signal faster than light. It is impossible to see the moment itself in advance if it has not yet reached us. If a star has already died somewhere thousands of light years away, but its last beam is still flying through space, The Earth lives in the interval between the event and its arrival, with no direct way to know what exactly is moving in our direction.
Yet the likelihood of such a strike remains extremely low. It is important to say this honestly. For a real threat, several conditions are needed at once. The source must be close enough, the burst must be extremely powerful, and its narrow beam must be directed almost exactly at the Earth. Most gamma-ray bursts are not directed at us. Most potentially dangerous events happen too far away. The Milky Way is huge, but such catastrophes are rare. Therefore, a gamma-ray burst is not a threat to wait for tomorrow. Its danger is not in the imminent inevitability, but in the fact that the universe is capable of creating events against which the planet has almost no warning. At the heart of this topic lies another mystery: why gamma-ray bursts are so different. Some flashes last moments, others last minutes. Some radiate energy as if their source violates the usual limitations of the models. In some, the afterglow disappears quickly. In others, it lasts for an unusually long time. Sometimes a gamma-ray burst is accompanied by a supernova, sometimes not. Sometimes it occurs in a distant, young galaxy rich in star formation, and sometimes its surroundings seem unexpected. This suggests that a whole family of cosmic catastrophes is hidden under one name.
The physics of a gamma-ray burst begins with gravity, but does not end with it. Gravity compresses the core of a star, or brings compact remnants closer together. Then, magnetic fields, accretion disks, relativistic jets, shock waves, and particle acceleration processes come into play. At the center of the event, there may be a black hole, around which an incandescent disk of matter rotates. Some of the matter falls inward, disappearing behind the event horizon, and some of the energy escapes along the axes of rotation. In these narrow channels, a stream is born that is able to pass through the stellar shells and escape into interstellar space. But exactly how energy is converted into gamma radiation remains one of the most difficult problems. Internal collisions within the jet are possible when fast layers catch up with slower ones. Magnetic reconnections are possible, in which the energy of the magnetic field abruptly transforms into the energy of particles and radiation. External shock waves are possible when the ejecta collides with the surrounding gas. Each mechanism explains part of the observed picture, but not all bursts fit into one simple scheme. Therefore, gamma-ray bursts remain not only a threat in theory, but also a laboratory of extreme physics.
They are important for understanding the early universe. Gamma-ray bursts are so bright that they can be detected at enormous cosmological distances. The light of some flashes travel to the Earth for billions of years. This means that they may serve as signals from epochs when galaxies were younger, stars formed differently, and the chemical composition of the cosmos was different from today's. Each distant gamma-ray burst is not just an explosion, but a trace of ancient stellar death that came from a time when the universe was different. The most distant gamma-ray bursts are especially valuable because they can indicate the death of the first generations of massive stars. These early stars could have been huge, hot, and short-lived. Their death enriched the cosmos with heavy elements, from which new generations of stars, planets, and complex substances were later formed. In this sense, gamma-ray bursts are associated not only with destruction, but also with cosmic evolution. They are traces of the processes that converted the original hydrogen and helium into a more complex universe.
They also have a connection with the origin of heavy elements. Neutron-star mergers can create conditions for the production of gold, platinum, and other heavy nuclei. In the short moment of the collision of super-dense matter, neutron fluxes are released, nuclear reactions are triggered, and part of the matter is ejected into space. Later, this matter may become part of interstellar clouds, new star systems, and planets.
In this way, events that look like pure catastrophe simultaneously become part of the chain of cosmic enrichment. For Earth, this creates a strange contrast. The same processes that may once have been involved in creating the elements needed for planets could become a threat to life elsewhere and at another time. The universe does not divide phenomena into useful and destructive. The same mechanism can be a source of chemical richness and a source of lethal radiation. A gamma-ray burst shows this duality especially clearly. It can be a trace of the birth of heavy elements, and at the same time, a potential impact on the atmosphere of a living planet. The so-called ultra-long gamma-ray bursts are especially mysterious. Some events last much longer than the usual long flashes. Their nature is not completely clear. Perhaps they are related to the death of unusual stars, to the prolonged feeding of the central engine, or to the destruction of a star near a compact object. Such bursts force us to reconsider the boundaries of classification. If a gamma-ray burst can last much longer than seconds or minutes, then the mechanisms that maintain the flow of energy may be more complex than a simple instantaneous catastrophe. There are also flashes that look too bright. Their energy, if the radiation is considered uniform in all directions, seems almost impossible. But it is the directivity of the rays that solves part of this puzzle. If the radiation is compressed into a narrow jet, the actual energy may be less than it first appears. However, this also makes the surge more dangerous for those on the release line. The beam does not simply reduce the overall energy problem. He turns a cosmic catastrophe into a targeted strike.
The Milky Way is not the most active place for such events. In galaxies with fast star formation, massive stars are born more often, which means that they are more likely to die in conditions suitable for long gamma-ray bursts. But our galaxy still contains massive stars, compact binary systems, and regions where the evolution of matter goes to extreme ends. The problem is that it is extremely difficult to understand in advance which system will create a gamma-ray burst and where its beam will be directed. Some massive star systems are sometimes referred to as potentially interesting candidates, but caution is needed. The presence of a massive star or an unusual binary system does not mean that it will necessarily create a dangerous gamma-ray burst. This requires precise conditions of rotation, mass, loss of outer layers, magnetic structure, and direction of the future jet. Even if the object looks dramatic, its real threat may be minimal. Therefore, it is more honest to talk not about a specific guaranteed danger, but about a class of rare events that can theoretically affect the planet.
If the gamma-ray burst were close enough and pointed at Earth, the first changes would occur in the atmosphere. Gamma photons would not pass freely to the surface in their entirety. Their energy would be absorbed and redistributed in the upper layers of the air. But it is this absorption that would trigger dangerous chemistry. The formation of nitrogen oxides could lead to ozone depletion and a change in the transparency of the atmosphere. The sky could change, not immediately as a spectacular catastrophe, but through the processes that unfold in the chemistry of the planetary shell. One of the possible effects is the formation of compounds that affect climate and light transmission. The atmosphere after such an impact could become chemically different. Changes in the ozone layer, an increase in ultraviolet light, possible changes in the nitrogen cycle, and the impact on cloud cover and the biosphere would all create a complex chain of consequences. The most vulnerable life forms would be the first to suffer, but the blow to the lower levels of ecosystems could spread higher. Such a catastrophe does not have to look like instant destruction. It can be the beginning of a planetary crisis.
That is why a gamma-ray burst is scary as a silent space impact scenario. It comes from an area that cannot be controlled. Its source may be far beyond the solar system. Its beam does not need mass to collide with the Earth. It does not leave an approaching body in the sky. It does not change the orbits of the planets. It simply brings the energy born at the end of the star. and this energy interacts with the thin shell of air on which life depends. The deeper gamma-ray bursts are studied, the stronger the feeling that they are on the border of several branches of physics. They are related to general relativity because space and time behave extremely near black holes and neutron stars. They are related to nuclear physics because the mergers of compact objects create heavy elements. They are associated with plasma and magnetic fields because jets are made up of accelerated matter and energy. They are related to the chemistry of the atmosphere because their radiation can change planets. One short signal connects the death of a star, the birth of elements, the structure of galaxies, and the fragility of life.
A gamma-ray burst also shows how limited the usual sense of distance is. In everyday understanding, thousands of light years seem to be completely safe. But for gamma rays directed by a narrow flux, even such distances can make a difference. Space is vast, but the energy of some processes is so great that the usual measure of danger ceases to work. Not everything far away is harmless. Not everything close is noticeable in advance. A gamma-ray burst destroys the simple certainty that distance always protects. At the same time, the Earth has existed for billions of years in a galaxy where stars explode, compact objects are born, and powerful flares occur. This means that such threats are not a permanent sentence. Life arose and developed despite cosmic catastrophes. The atmosphere, magnetic field, distances, and the rarity of events create natural protections. But this protection is not absolute. The history of the planet is not only internal processes, climate and geology, but also the external galactic environment, in which events of colossal power sometimes occur.
One of the unsolved mysteries is the exact frequency of dangerous gamma-ray bursts in galaxies like the Milky Way. Estimates depend on many factors: the rate of formation of massive stars, the proportion of stars with the desired rotation, the properties of binary systems, the width of the jets, the chemical composition of the galaxy, and the distribution of sources. The narrower the beam, the less likely it is to hit the Earth, but the stronger the impact on the direction line. The rarer such events, the more difficult it is to evaluate them from observations. We see mainly those bursts whose rays are directed towards us, which means that the sample itself is already distorted by directionality. There is also the problem of hidden events. If a gamma-ray burst is not aimed at Earth, it can be much more difficult to see. Its afterglow or associated phenomena may be visible, but the main gamma ray goes in the other direction. This means that there are more such explosions in the universe than are directly registered. The visible picture is only a part of reality. Gamma-ray bursts are a reminder that the cosmos doesn't have to reveal all events in the same way. We only see catastrophes whose geometry allows them to send a signal in our direction.
The future of the study of gamma-ray bursts lies in rapid detection, multi-band observations, and the search for gravitational waves from mergers of compact objects. When a short burst is associated with a neutron star merger, the signal can come not only in the form of light, but also in the form of ripples of space-time. This opens up the possibility of studying one event in several ways at once. Light shows energy emissions and chemical composition. Gravitational waves reveal the movement of masses, and the afterglow shows the interaction of the jet with the environment. The more such links are found, the clearer the nature of these outbreaks will become. But even with the development of observations, the main feature will remain the same. It is impossible to prevent a gamma-ray burst. No amount of technology can stop the collapse of a distant, massive star or change the direction of the jet if the event has already occurred. The most that can be done is to understand the risk, look for potential sources, study atmospheric consequences, and build models. In this sense, a gamma-ray burst is different from many terrestrial threats. It is uncontrollable. It can only be understood.
And there is a cold truth in this understanding.
The Earth is not isolated from the universe. It is not behind an invisible wall separating life from cosmic processes. Every planet exists within a galaxy, among stellar births and deaths, among explosions, particle flows, gravitational collisions, and radiation from the depths of time. Life on the surface depends on a delicate equilibrium, and this equilibrium can be disrupted by an event that began far beyond the solar system. A gamma-ray burst is one of the most striking symbols of such vulnerability. He doesn't just show how stars die. It shows that the death of a star can have consequences far beyond its system. It turns the end of a single object into a signal that can cross the galaxy. He reminds us that cosmic distances are enormous, but not always enough to completely separate one region of the universe from another.
If a living planet ever finds itself in the path of such a beam, it may not see the approach. There will be no slow fire on the horizon. There will be no object growing in the sky night after night. There will be no time to wait. Radiation will come first. Then the chemistry of the atmosphere will begin. Then the light that reaches the surface will change, and only after that will the consequences become part of the history of the planet. The biggest mystery of gamma-ray bursts is not only in their origin, but in how deeply they are connected to the overall fate of the cosmos. They are born where matter reaches the limits of density, velocity, and temperature. They are visible billions of light years away. They can create heavy elements. They can reveal the properties of early galaxies, and theoretically, they can change conditions on planets far from the explosion site. Destruction, birth, light, gravity, and time are combined in one phenomenon.
Therefore, a gamma-ray burst is not just a topic about a space threat. It's a story about how powerful the universe can be when a star reaches its ultimate limit. This is the story of a ray that can cross the darkness faster than any warning. This is a story about a fragile atmosphere that protects life from radiation that was born in the catastrophe of a distant world. And it's a story about the fact that the scariest events in space don't always look scary in advance. Sometimes they come as a short flash from the depths of space, and by the time it becomes visible, nothing can be changed. Yet, the most disturbing aspect of a gamma-ray burst is not that it can destroy everything instantly. The real danger is much more complex and colder. The Earth would not necessarily turn into a lifeless world in 1 second. The oceans would not disappear all at once. The continents would not have shattered with a single blow of light. But the planet's invisible defenses could be severely damaged. The upper atmosphere would take over the flow of gamma radiation, and it is there that a chain of processes would begin, the consequences of which would spread down to the surface.
The ozone layer is one of those things that are almost invisible, but on which everything depends. It does not make the planet brighter, does not create mountains and seas, does not look like a grandiose cosmic structure. But without it, solar ultraviolet would become much more dangerous. If a powerful gamma-ray burst were to destroy a significant portion of the ozone, the Earth's surface would be exposed to increased hard radiation. It wouldn't be one short flash of pain for the planet. This could be a lasting change in conditions that would last for months, years, or even longer as the atmosphere gradually regains equilibrium. The most vulnerable would not necessarily be the largest forms of life. The blow could have started with something that would normally go unnoticed: microscopic organisms, the upper oceans, those living systems that stand at the base of food chains. If they weaken, the effects will begin to rise higher. Nutrition will change, water chemistry will change, and the life of marine ecosystems will change. On land, increased ultraviolet radiation could damage cells, seeds, plant tissues, and disrupt the development of organisms. Such a catastrophe does not necessarily look like a single blow. It may look like a slow fading of stability.
That is why a gamma-ray burst is more frightening than many other space threats. The asteroid leaves an impact, a crater, dust, fire, and a direct impact trail. A supernova leaves behind an expanding envelope and powerful radiation. But a gamma-ray burst may be an almost silent message from deep within the galaxy. His main blow is not a stone, not a plasma wave, not a red-hot substance. It is an energy that comes in the form of light that cannot be seen with the eyes and cannot be stopped by a wall. It passes through the cosmic void without losing direction until the atmosphere of the planet is in its way. Earth has already survived billions of years in a galaxy where stars are born and die. This means that the very possibility of life proves that such catastrophes are rare. But rarity does not equal impossibility. Space does not have to be safe just because it has remained calm for a long time. The history of the planet could have passed between great flares, between distant collapses of stars, between rays that went in other directions. Perhaps the Earth has been just lucky with the direction many times. Perhaps the most terrible emissions passed by without touching the thin blue shell of the planet.
It is especially important to understand that a dangerous gamma-ray burst must coincide with the Earth almost perfectly. The beam should be directed exactly in our direction. The source should be close enough. The surge should be powerful enough. All these conditions together make the scenario rare. But it's this geometry that turns a gamma-ray burst into a phenomenon where direction may be more important than distance. In another part of the galaxy, a star may die, and for most worlds, it will be a distant flash. But for a planet directly on the emission line, this could be the beginning of a new era in the atmosphere. This is one of the deepest mysteries of gamma-ray bursts. They don't just explode, they choose a direction through the physics of their jets. At the center of a dying star or merging neutron system, a region is formed where matter, magnetic fields, and gravity work at their limits. The flow of energy breaks out along the axes, breaks through the surrounding matter, and goes into space. Why does the jet have this shape? Why is it narrow and bright in some bursts, while in others it is wider and weaker? Why do some bursts seem too powerful for standard models? The answers are still incomplete. Each new gamma-ray burst adds data but does not completely close the mystery. Some events have a strange afterglow. Others last longer than expected. Still others occur in conditions where their origin is difficult to explain. Sometimes the signal seems short, but its surroundings resemble a different type of disaster. Sometimes the burst is so far away that it becomes not only an explosion, but also a window into the early universe. This makes gamma-ray bursts both a threat, a trail of stellar death, and a clue to the history of the cosmos. Through them, you can understand how the most massive stars die. Through them, you can find out how black holes are born. Through them, you can see how neutron-star mergers create heavy elements. Through them, you can feel how bright the ancient universe was when the first generations of stars began to change its chemical composition. One short signal can contain the history of matter that has gone from a primordial gas to an extreme explosion. And there is a dark beauty in this. A gamma-ray burst is devastating, but it is not random chaos. It is born from the laws of physics, from gravitational collapse, from preservation of rotation, from magnetic fields, from the motion of matter almost at the speed of light, from collisions of particles, shock waves, and radiation. It does not disturb the order of the universe. It shows what this order becomes in the most extreme conditions. For Earth, it all boils down to one question. Could such a flare ever be directed at us? The honest answer is that it is not known for sure.
There is no confirmed close source that is guaranteed to create a deadly gamma-ray burst for Earth. But it is impossible to completely exclude the possibility itself on the scale of a huge time. The galaxy lives for billions of years. Stars continue to evolve. Compact objects continue to approach each other. Somewhere, systems are already forming, the finale of which will be more powerful than anything that can be seen in the ordinary starry sky. The future of such objects is already laid down in their mass, rotation, and environment. A massive star cannot stop its journey to the final if the internal fuel is exhausted. Neutron stars in a close binary system cannot maintain their previous orbit indefinitely. Black holes do not stop changing the space around them. The cosmos is constantly preparing events that could happen in thousands, millions, or billions of years. Most of them will go far. Most will not touch the Earth. But the very possibility shows that life does not exist in motionless silence, but inside a vast galactic environment where peace is always temporary. And if one day such a ray does cross the path of the Earth, humanity will not see its approach in advance. It will not be a slow threat growing in the sky. There will be no point of fire that can be tracked for years. There will be no final countdown. Gamma radiation will bring news of the catastrophe at the same moment it causes it. Space will not give time for an argument, for waiting, for preparation. The signal and the blow will come together. But that's why gamma-ray bursts are so important for understanding our place in the universe. They show that the Earth is protected not by an absolute wall, but by a delicate balance. The atmosphere, the magnetic field, the distances, the rarity of events, the direction of the rays, all this together creates the conditions in which life was able to survive for billions of years. But this balance is not an eternal law. It exists inside the cosmos, which is much more powerful than any planet. A gamma-ray burst is a reminder that the strongest threats don't always look like huge objects. Sometimes the danger has no form. Sometimes it does not cast shadows. Sometimes it does not approach as a body, but comes as a flow of energy born in the last moment of a distant star. It can travel thousands of light years, pass through the dark regions of the galaxy, and reach a planet that never knew that an event that could change its future had occurred somewhere long ago.
And yet, in this story, there is only fear. It has a scale. Gamma-ray bursts help to reveal the structure of the universe. They show how matter behaves on the edge of the impossible, how black holes are born, how super-dense stellar remnants collide, how heavy elements are created, and how distant galaxies make themselves known billions of years later. They are some of the most powerful signals that space is capable of sending into space. Each such burst is the final phrase of an object that can no longer exist in its previous form. The star dies, the core collapses, the space around it shrinks, the matter accelerates, and from this catastrophe, a ray is born that can cross the universe. For one system, this is the end. For distant worlds, it is a signal. For science, it is the key to extreme physics. For a living planet on the strike line, this is the possible beginning of a disaster.
The Earth remains safe for now, not because space is safe, but because dangerous conditions must coincide too precisely. This is an important difference. Our planet exists in a fortunate interval, far from most monstrous explosions, out of the path of known death rays, protected by an atmosphere, surrounded by the solar system,
and separated by vast distances from the most active regions of stellar death. But the universe is not static. Everything moves, ages, draws closer, collapses, and is born anew. A gamma-ray burst makes you look at the night sky differently. Future catastrophes may lurk among the calm stars. Among the distant points of light, there are systems whose finale will be so powerful that its signal will be able to pass through the galaxy. Many of these events will never touch Earth. Their rays will disappear into the void. Their afterglow will dissolve into the depths of space. Their energy will be only a brief flash in cosmic history. But the very possibility of such a blow makes the universe not only beautiful, but also alarming.
This is the main mystery of gamma-ray bursts. They are too short to seem eternal, but too powerful to be a random detail. They last seconds, and the consequences of their origin are associated with millions and billions of years of stellar evolution. They are born in destruction, but they help to understand the creation of the elements. They can be seen from the edge of the observable universe, but their threat depends on a thin line of direction. One ray, one axis, one angle, and an event taking place far away acquires significance for the whole planet. If such a day never comes, gamma-ray bursts will still remain some of the greatest warnings of the cosmos, not because they will necessarily destroy the Earth, but because they show the limits of planetary security. They remind us that life does not exist separately from the universe, but within it. Every breath, every ocean, every layer of the atmosphere is protected by a delicate balance that has formed amidst stellar explosions, radiation, gravity, and time.
And when a distant gamma-ray burst erupts deep into space, it speaks of the most extreme end of matter, where the star can no longer resist its own mass, where neutron remnants merge in the last fall, where energy is bursting out with such force that its trace can be seen billions of light years away. It's not just an explosion. This is the moment when the universe shows its true power. For Earth, this light almost always remains only a distant signal. It comes weakened, safe, turned into data about a distant catastrophe. But somewhere in the very nature of this phenomenon, there remains a cold question. What happens if one day the distance is insufficient and the direction is too precise? The answer to this question does not require unnecessary words. If the beam comes, there will be no warning. If the atmosphere takes a hit, the effects will begin from above and slowly descend to life. If the ozone shield is destroyed, the planet will feel not only the power of a distant star, but also the fragility of its own defenses.
Thus, a gamma-ray burst becomes not just a topic about space danger. It becomes a story about the boundary between life and the universe, about how far the death of a star can reach, about how a few seconds deep in the galaxy can make a difference to millions of years of planetary history, about the fact that even the most peaceful world exists under the sky, where sometimes flashes are born that can change everything. And while the Earth continues to revolve around the Sun, as long as the atmosphere maintains equilibrium, while distant stars seem motionless, somewhere in space, processes are already underway, the finale of which cannot cancel. Massive nuclei are shrinking, neutron stars are getting closer, magnetic fields twist, matter falls into regions where conventional physics becomes extreme. And one day, a gamma-ray burst will flare up again somewhere.
Perhaps his beam will go into the void. Perhaps he will pass by all the worlds. Perhaps it will only be a distant signal that will tell about the death of a star and the birth of a black hole. But its very power will remain a reminder. The universe doesn't have to be quiet to seem calm. The most terrible events can happen far away. The strongest blows can come without sound. The shortest flares can leave the longest effects.
And if one day a real gamma-ray burst comes to Earth from the depths of the galaxy, it will not wait until it is noticed. It will not warn. It will not approach slowly. It will just reach the atmosphere. And then it will become clear how thin the border was between a calm sky and the power of a distant dying star.